Chapter 8 is the last chapter of the magnetism portion of the course. Afterwards, we're just going to look at different types of life physics and medical physics applications related to electricity and magnetism together. So Chapter 8 has to do with electromagnetic induction. In this chapter, we're going to first go through a brief recap of magnetic forces and fields, essentially the Biot-Savart law as well as Ampere's law. Then we're going to take a look at induced currents and Faraday's law, where Faraday's law is the last Maxwell's equation to look at. We then have induction, energy, and Lenz's law, which is a part of Faraday's law. We'll take a look at inductance itself, magnetic energy, as well as induced electric fields. Then we're going to go back to circuits, where we take a look at alternating current, LC and RLC circuits. And of course, after that, we'll take a look at applications individually as units and chapters. So a quick review in chapter 8.1. First, we took a look at the magnetic force. Keep in mind the rules for magnetic force and the direction. We use the right-hand rule. So in terms of this, we have the equation for magnetic force, which is a cross product. So in terms of looking at the angle between the velocity of the charge, or where the current is going, as well as the magnetic field, it's going to be QVB sine theta, where you get the maximum force if your sine theta is equal to 1. So that's when it's 90 degrees. So in terms of applying the right-hand rule, we know that we point our fingers in the direction of V, and then we wrap our fingers around towards the vector B, and whatever direction your thumb is pointing in, that's the direction of your magnetic force. After that, we took a look at the Biot-Savart law. So think of it like how in Coulomb's law, we have dE due to a differential charge element dQ. We now have dB, a differential magnetic field element, because of a small differential current element dL. So keep in mind it's a vector quantity. So at the very end, your magnetic field solution should have a direction. Instead of using the Biot-Savart law, we can use Ampere's law as a shortcut or an easier way of determining the magnetic field if your current and the object that you're looking at is symmetrical. So Ampere's law relates the magnetic field to its source. So if we have consistency within the magnetic field and we know the path length traveled of the magnetic field, then we are able to factor out B, especially if it's constant, and then figure out the path length, which is the integral of dr. And then we just need to figure out what the enclosed current is, or encircled current, from the Amperian loop, and we'll be able to determine what the magnetic field is. Okay, so looking at chapter 8.2, we now want to go through an overview of electromagnetic induction. So first, the big picture. Electromagnetic induction is a phenomenon where a changing magnetic field around a closed circuit induces an electric current within the circuit. So the greater the rate of change in your magnetic field, the greater the electric current and the greater the voltage. So that's a very important definition to understand. Alternating current AC is something we'll now bring into the picture. Basically, when both the magnitude and the direction of the current and voltage changes with time, then you have an alternating current. In a direct current, neither changes with time and they're always constant. So from that, we now ask, why is E&M induction important? So every modern device has electric circuits, and EMF is going to be required for a current to flow. And that can come from a battery or some kind of electric generating station, which is a little bit more common, like a generator. So this converts other forms of energy into electric energy. The next question I want to ask is, how do we increase the magnitude of the current or the voltage? We can either use strong magnets, we can use more magnets, we can increase the number of turns on a solenoid, and we can either move the magnet or the coil, or both, faster. And you can also insert a soft iron core into the solenoid. So there are various ways to be able to increase the magnitude of the current and the voltage. So back to the electromagnetic induction, energy conversion is usually done through EM induction. So if the magnetic flux through the circuit is going to change, an EMF and a current will be induced in the circuit because of that change. In a power generation station, the magnets are going to move relative to the coils of wire that exist, and that causes a changing magnetic flux in the coils, and therefore that produces an EMF. So over the next few slides, we're going to go through, and in the next few subchapters, we're going to go through how changing different components will affect the magnetic field. So for laws of induction, the central principle of EM induction is Faraday's law, which is a Maxwell's equation. It helps relate EMF, or a voltage, to a changing magnetic flux. Another law, which is called Lenz's law, helps us predict the direction of an induced EMF and current. So Lenz's law is a portion of Faraday's law, which helps us determine the direction of an induced EMF. So all of this leads to us towards a set of Maxwell's equations that help describe the behavior of electric and magnetic fields in any situation. In chapter 8.3, we want to take a look at induced currents and Faraday's law. So before we get into Faraday's law, we want to take a look at the history of how people were able to determine that currents could be induced, take a look at magnetic flux, and then take a look at the actual law itself. So in 1831, Michael Faraday and Joseph Henry each independently found that electric currents would arise when they were subjected to a changing magnetic field. And the key word here is changing, because changes did not take place if the magnetic field was constant. So what Faraday used was a cardboard tube, represented here, with an insulated wire wrapped around it to form a coil. And then he had a magnet that was passed through the coil, and he noticed the change in an ammeter. So in the first experiment, we'll actually go through several experiments to determine what kinds of behavior is involved when it comes to EM induction. So in the first experiment, we have a bar magnet that's being moved. And the bar magnet is either stationary in this case, moving away or towards the coil over here between these two, and moving at different speeds. So in terms of this, no change is registered in the ammeter if the magnet is stationary. When we move it either towards it or away from it, then the ammeter is going to register something at a certain magnitude. If we change the speed in which we move the bar magnet away or towards the coil, then the magnitude of the change is going to increase. So basically, the faster we move the bar magnet away or towards the coil, the stronger the current is going to be. In the second experiment, they wanted to test to see if the same effect would take place if you're keeping the magnet stationary but moving the coil instead. And the exact same results were shown. So it doesn't matter if you're moving the coil or the magnet. As long as they're moving towards and away from each other, there will be a change in the induced current. In the third experiment, what happens if we replace the magnet with a current-carrying circuit? So if we replace the magnet with a current-carrying circuit here, then we have to understand that a current-carrying wire will generate a magnetic field. So if we move the coil towards another coil that's stationary, it will induce a current in this coil as well, because this one on the left will create its own magnetic field. In the fourth experiment, if the stationary circuit had an on-off switch, and basically you have these two coils that are just sitting there stationary, but this one has a switch that you can turn on and off. If you turn this on and off, will it affect and induce a current in the adjacent coil? And the answer is yes, because by turning something on and off, you are initiating a change in the current and therefore a change in the magnetic field, which causes a change in current in the adjacent coil. So what do these experiments show? It shows that a changing magnetic field, no matter where it's coming from, will induce an electric current. And so electromagnetic induction is when electrical effects come from changing magnetic fields. So now that we know that this does take place, we need to find a way to quantify this. And so we need to understand what magnetic flux is and what an induced EMF is. First, magnetic flux is going to be quantified by phi b. So similar to electric flux, we have phi e, we now have phi b for this. Previously, we do know that magnetic flux through any closed surface is 0, but what if we have an open surface? Similar to electric flux, magnetic flux is going to be the integral of the magnetic field over a certain surface. So it's the exact same equation, but we replace E with B. So here's a visual representation of magnetic flux. Instead of determining how many electric field lines penetrate a surface, we want to see how many magnetic field lines penetrate a surface. So we have a circular wire loop in the magnetic field of a bar magnet. As the magnet moves closer, more magnetic field lines are going to penetrate the surface, and therefore there's going to be a larger induced current. With electromagnetic induction, we're most interested in the flux going through a surface that's bounded by a circuit. So it can be any surface bounded by the loop. So if we actually have a flat surface in a uniform magnetic field, we can rewrite the magnetic flux equation and get BA cos theta, which is just the dot product of B and A. Oh, so going back, similar to before with electric flux, if the angle between the field and the normal to the area is parallel, then we get maximum flux. So basically, when the field is perpendicular to the area. So now we take a look at Faraday's law. A current without a battery must have an induced EMF, and that can be spread through conductors within a circuit. For Faraday's law, the induced EMF is proportional to the rate of change of magnetic flux through any surface bounded by that circuit. So Faraday's law itself is equal to this, where you have epsilon E for the EMF is equal to negative d phi b over dt. So it's the negative of the change in magnetic flux over a certain amount of time. This negative comes from Lenz's law, and we'll explain that in the next section. So when do we use Faraday's law? We should see if the problem involves a circuit and determine the cause of changing flux. We should see if there's a changing magnetic field, a changing area, or a changing orientation of a circuit relative to a field. Once we can find an appropriate expression for the magnetic flux, we can solve and then use Faraday's law to find the induced EMF. So always make sure that your answer makes sense through both qualitative and quantitative measurements. In our first problem, we're going to take a look at the magnetic flux of a solenoid. A solenoid of circular cross-section has a radius of r, consists of n turns per unit length, and carries a current of I. Find the magnetic flux through each turn of the solenoid. So we'll list out what we're given. We know we have a solenoid. We know there's going to be a magnetic field within that solenoid. We know that there's going to be n turns per unit length. And we see that B is going to be perpendicular to the cross-sectional area. So that means that magnetic flux is going to be BA cos theta where cos theta is equal to cos 0, which is equal to 1. And so therefore the flux is going to be B times A. So just keep in mind that it's cosine of 0 because even though the magnetic field is perpendicular to the cross-sectional area, our surface normal vector is going to be parallel to B. So that's why it's 0. So same as when we were analyzing electric flux. Now that we have this, we can solve. A solenoid field is given by B equals to mu naught Ni, as we did last chapter. Now the cross-sectional area is A equals to pi r squared. So now I have the total flux being equal to mu naught Ni pi r squared. And that is our answer for magnetic flux through each turn of the solenoid. In problem 2, we have a long straight wire that carries a current of I. A rectangular wire loop of dimensions L by W lies in a plane containing the wire. So let's just start by drawing a diagram as we go along. We have a long straight wire. It carries a current of I. And that means it's going to have a magnetic field that goes this way. Okay, then we have another one. We have a rectangular wire loop, and it lies on a plane containing the wire. So that means we'll just assume that it's on the same plane. So that's our rectangular wire loop of width W and length L. The closest edge is a distance A from the wire, so we know this is going to be A. Oops. Its dimension L is parallel to the wire. Find the magnetic flux through the loop. So in this case, we really have to look at some different aspects. First, we want to split the area into thin strips of dr. So we're doing that so that we can analyze each section because each part of the loop is a different distance away from the wire. So we're going to split this up. So we have a section dr over here. And this is going to be a distance r away from the wire. So this is then going to become our area element for integration. So if we split the area into thin strips of dr, what we can do is use dA is equal to L dr, and then we have to integrate from A to A plus W. So the magnetic field lines are going to point where the rectangular loop is. So we end up with magnetic flux. We're going to start solving. We do have flux being equal to the integral of B dotted with dA, which is equal to B. Oops. B dA cos theta. We know it's going to be cosine of 0, which gives you a value of 1, so you end up with B dA for this. And from before, we also know that the B field of a wire is mu naught I over 2 pi r. So we can use readily available equations and then solve for magnetic flux. So this is then going to be mu naught, the integral, just going to make this a little bit easier. The integral from a to a plus w of mu naught I L dr, because we know that's dA. Then we have 2 pi r at the bottom. We factor out the constants. And we end up with mu naught IL over 2 pi times the integral of a plus w of dr over r. That's going to give us ln of r as the integral solution. So we have mu naught IL over 2 pi, and we have ln of a plus w over w. And that is the answer for our magnetic flux. In this problem, there's a wire loop of radius 10 centimeters with a resistance of 2 ohms. The plane of the loop is perpendicular to a uniform magnetic field B that's increasing at 0.10 Tesla per second. Find the magnitude of the induced current in the loop. So what are the steps required for this? First, we should probably find an expression for the magnetic flux, and then we should use Faraday's law to figure out the induced current. So let's go for magnetic flux. So we have but we know B is going to be parallel to dA. So we have B dA cos 0 equals to B dA. We end up with the flux being equal to the integral of B dA. So we have B is the integral of dA, but we know that the surface area is simply a circle, so it's pi r squared. So we have B pi r squared as our flux. Next, we want to apply Faraday's law and find the induced current. Now, you could have started here because we would have to apply Faraday's law to find the induced current. If you were to start here with Faraday's law, then you would have written epsilon for the induced voltage is equal to negative change in magnetic flux over dt. And from there, you'll know you have to figure out magnetic flux first. But since we did that already, we can simply just have minus d over dt of B pi r squared. And that gives us negative pi r squared dB. That was kind of messy. Negative pi r squared dB over dt. Now we know that the magnetic field is changing at 0.10 Tesla per second. We know that the radius is 10 centimeters, or 0.1 meters. So we can immediately just solve. We have minus pi, 0.1 squared, and then 0.10 Tesla per second. So that gives us negative 3.14 millivolts. And we are just worrying about the magnitude of the induced current. So in this case, we can just say this is 3.14 millivolts. And then we can move on to current, where V is equal to IR. or epsilon is equal to IR. So that means we have I equals to epsilon over R, which is 3.14 millivolts over the resistance 2.0 ohms. And that gives us 1.6 milliamps as our induced current. We're now going to move on to induction, energy, and Lenz's law. So first of all, we have to ask, where does the energy come from for an induced current? So because we have to change the magnetic field in order to cause an induced current, the energy is going to be in the work done to cause that change in the magnetic field. So the conservation of energy is going to determine the direction of the induced current. So on the left diagram, we're going to see a bar magnet and a loop with a current going through it. So in terms of this, we're going to be moving this bar magnet towards the loop, and there will be changes, and a current will be induced. So how do we try and picture what kind of change is taking place in terms of the current? So in the left, we see what is happening, and then on the right, we're taking a general look, and we see that the loop acts like a magnet with the north pole to the left and a south pole to the right. So to visualize this, we have to see what kind of magnetic field the loop produces apart from the magnetic field from the bar magnet. So on the right, we know that we wrap a current around using the right hand rule, wrap our fingers around the current, and we know that the magnetic field is going to point towards the left. So we get this. So the fingers in the direction of the current point the thumb in the direction of the north pole of your imaginary magnet. So that loop is going to act like a bar magnet with the north pole to the left. Next, what happens if we reverse the direction of the induced current? So instead, we now wrap our fingers around forward, and then that means our, I guess like this. And that means our thumb is going to point now towards the right. And so the loop is now going to act as if there's a south pole on the left side. So what does this mean? It means that if you have your north pole here facing towards the loop, and now your loop itself has an imaginary bar magnet with the south pole facing towards the left, it means it'll be more difficult to pull the bar magnet away from the loop. So now we move on to Lenz's law. This kind of phenomenon is exactly what is summarized in Lenz's law. So the direction of an induced EMF or current is such that the magnetic field created by the induced current opposes the change in magnetic flux that created the current. So mathematically, it's the minus sign that we see in Faraday's law because the induced EMF is going to be in the direction opposite of the one that's created by the change. So what is emotional EMF? When a conductor moves through a magnetic field, the origin of the induced EMF is in terms of the magnetic force on what carries the charge. So this is the case of motional EMF. It shows that Lenz's law requires energy conservation. So to explain this better, we're going to take a look at a few examples afterwards to see how these changes take place and what the induced direction would be in for the current. So the first example we're going to go through is a square conducting loop of side L and a resistance R that's pulled with a constant speed V out of a uniform magnetic field B. So this is our loop. We're trying to pull it out of a magnetic field in this gray region over here. So the magnetic flux through the loop is going to change because less and less of the magnetic field is going to be enclosed within that loop. The induced EMF is going to drive the current because the magnetic field is changing. The energy itself is going to be dissipated as heat while things move apart from each other. And it means that the agent that's pulling the loop will do the work to cause an induced EMF. So we want to be able to explain every single thing that's happening in this diagram. So first, the magnetic flux through the loop is changing. The induced EMF drives the current, and energy is dissipated as heat. But we know that whoever is pulling the loop away from the field is doing the work. And this motion of pulling the loop is going to move free electrons through the magnetic field. The magnetic force is known as Q, V crossed with B on these electrons, and that's going to be in the direction downwards. This causes an upwards current that's clockwise around the loop, which is why you see a loop going in the clockwise direction. The magnetic force on the conductor of a length L, so assume all these are L, is F equals to IL crossed with B. So on the right-hand side, we know that there is no magnetic field, so it's zero valued. So it means that there is no force acting on this. So the magnetic force only exists on the left side. Doing a deeper analysis of the force acting upon the loop, the magnitude of the force on the left-hand side is going to be ILB. The right-hand rule is going to show that it points to the left. So basically we can form the current and see where it points to. To calculate this induced current, we first need the induced EMF. So we know that the magnetic flux is going to be BLX for B crossed with B dotted with A. And as the loop moves, X is going to decrease at a rate of negative V. The flux can then be written as minus BLV for BL, and then V is dx over dt. So we have this form. Continuing on from this, we can apply Faraday's law. So equations for motional EMF, we have Faraday's law giving epsilon, or induced EMF, equals to BLV. We know another way to represent epsilon, and so that's going to be I equals to V over R, or I equals to epsilon over R, and we get BLV over R. So if we combine both of these equations together, we can actually multiply I and E to get BLV squared over R, and that gives us the electric power that's dissipated in the loop. So you'll notice that there's another way to write this as well, and because we also have an equation for force and power, power is equal to some force dotted with V, and then we have F equals to ILB. So the mechanical power that's applied to pull the loop is given as P equals, sorry, that's not a dot, it's multiplied. P is equal to F times V, and that's equal to BLV squared over R. So you'll notice that these two expressions are the same. This means that the work done by the agent pulling the loop ends up heating the resistor. So therefore, we can verify that all of the energy is conserved. So next, through Lenz's law, we want the resulting or induced magnetic field to oppose the change in flux. So that's very important. We're going to go through some examples to try and explain all of this. There's 4 in total. So first, we're going to go through the left example. Basically, we have a bar magnet with the north pole pointing downwards, and we're moving it towards a current-carrying wire. So the North Pole has magnetic field lines coming out of it. That means more magnetic field lines will penetrate the loop, so there's an increasing downwards flux. If there's an increasing downwards flux, then that means the induced magnetic field must be upwards so that we can oppose this change in flux. So we know that there's an increasing downwards flux. We want to compensate by making sure there's an upwards induced magnetic field. So from that, we decide what direction the current's flowing in. In order to have an upwards induced magnetic field, we point our thumb up, and we know that the current has to go in the counterclockwise direction, viewing from the top. Now, on the right side, we have the south pole of the magnet facing downwards, and we're trying to move it away from the loop. So if we're moving the the bar magnet away, then there's going to be less and less flux going through the loop. So there's a decreasing upwards flux because it's pointing up for the direction of flux. So if we have a decreasing upwards flux, that means we should have an increasing upwards flux to keep everything the same and cancel things out. So that means the induced field must point up, and therefore the current is still going to go counterclockwise. Next, we have two other scenarios. We have the North Pole facing down and moving away from the loop. So the North Pole has magnetic field lines going down, so there's a downwards flux. But as we're moving it away from the loop, there's a decreasing downwards flux, which means we need to be able to have an increasing downwards flux in order to compensate for the change. So this means we must have a magnetic field, an induced magnetic field pointing down, and so the current to create that is clockwise. Now we look at the second example here, or technically the fourth one. We have the South Pole pointing down, and we're pushing it towards the loop. So for the South Pole, we know that it's going to attract the magnetic field lines, so therefore the magnetic field lines are going, or the magnetic flux is going to be upwards through the loop. As we're pushing the South Pole of the magnet closer and closer to the loop, we end up having an increasing upwards flux. So how do we compensate this? We can have a way to have an increasing downwards flux to oppose this. So we make sure our magnetic field points down, and that means our current is going to go clockwise. So those are just 4 examples of how to compensate for a change in magnetic flux from the 4 different examples. So let's go through what happens within an electric generator. A generator is a system of conducting loops over here in a magnetic field. So the mechanical energy is going to rotate the conductors, and this changes the magnetic flux and therefore causes an induced EMF. So this whole thing spins around, causing a change in the magnetic flux, which then causes an induced EMF. So specifically, this is an example of what we call an alternator. One conducting loop rotates in a magnetic field to produce an EMF. It's the angle over here, phi, that changes to produce a changing magnetic field. So here we have a rotating slip ring, these two over here, connected to the terminals A and B. An alternating EMF is generated that varies sinusoidally with time. And it's the opposite of how a motor works, and it's electrical to mechanical instead. Now, just to explain the alternating EMF a little bit more, we have a graph over here where we have the motional EMF and the flux over time. The blue one is the motional EMF, and the brown goldish one is the magnetic flux over time. So in terms of the loop that's seen from the end on, remember it's rotating along its axis. As it's rotating, we have flux decreasing the most rapidly when it's flat or 90 degrees, and we get the largest possible EMF. And then flux at its most negative value, or basically when it's straight on, is going to be 0. So the flux then goes back to a flat rate, or the loop goes back to a flat orientation, but now pointing in the opposite direction. So you have a larger magnitude, but the largest negative EMF. And of course, when it goes back to a straight up, it's going to be 0. So now we want to take a look at some quick applications. First, how do credit cards work? What happens when we swipe a credit card? We need to have the magnetic strip over here come into contact with the device that reads the card. This magnetic strip usually contains ferromagnetic material. It's going to store info in regions of different magnetization. So every time you swipe the credit card, it induces a current in the reader's coil over here. and that is going to extract information as an electrical signal to be processed by a computer or software. Now for eddy currents. Eddy currents, or also known as Foucault's currents, are loops of electric current induced within conductors that are induced by changing magnetic fields. So in the picture on the left, there's a metallic disc rotating in a magnetic field perpendicular to the plane of the disc. So here we have the magnetic field going in, and there's rotation along the disc in a clockwise fashion. But this type of magnetic field is confined to a limited portion of the disc area. An EMF is going to be induced in the center segment, and then they are going to provide return conducting paths or charges that are displaced in other sections. This causes a circulation called an eddy current. So because we've gone through all of the equations throughout this course, we can sum up all of the equations through Maxwell's equations. So the four main equations that we were talking about at the beginning of this course have now been covered. Although Maxwell didn't discover all of these equations, he was the one who put them all together. So he recognized their significance, and these are extremely important in the application of E and M waves. So these are the four equations. We have Gauss' law for an electric field. We have Gauss' law for a magnetic field. We have Faraday's law, and we have Ampere's law. So note that Ampere's law looks a bit different here. And the reason why it's different is because Maxwell introduced a new term into Ampere's law called the displacement current. And that's because any changing electric flux is going to result in a magnetic field. So these help tie together all of the concepts within electricity and magnetism. There are various forms of each of these. We never really went into detail with all the calculations for each, but in general, the four Maxwell's equations are commonly used in different forms for all applications of E&M. Okay, in this problem, we have an electric generator that consists of a 100-turn circular coil, 50 centimeters in diameter. It's rotated at 60 revolutions per second to produce a standard 60 hertz alternating current. Find the magnetic field strength needed for a peak output voltage of 170 volts. The peak standard in 100 is 120 volt household wiring. Okay, so first we have to state some knowns and equations, and we also have to maybe draw a diagram just to understand everything that's going on here. So first, we can assume we have an electric generator that looks like this. This is going to be wires that lead to the load. It is going to rotate. So I have my planar axis here, and so we have rotation around this, and that rotation takes place at omega equals to 2 pi f for the angular frequency. Now the magnetic field is going to pass through this, so we have B for the magnetic field. We also have a coil area. So we can set this area, which is pi r squared, because it's circular. Okay, so next, at the very end of the day, we want to find the magnetic field strength required. And in order to do that, we still need to find voltage. And in order to find voltage, we have to apply Faraday's law. But before we apply Faraday's law, we need to know the change in magnetic flux. So that means we have to figure out magnetic flux first. So let's start with magnetic flux. We have a uniform field. There's a flat circular area. So that means the flux through one turn of the coil is given by, I'm just going to do flux 1 for one turn. It's equal to B dotted with A. And that's going to give us B times A cos theta. A is pi r squared, so we have B pi r squared cos theta. Now, we can't just assume that cos theta is either 0 or 1 in this case. Theta is going to change as we rotate. So that means we have to do another analysis. We're going to then take a look at Faraday's law. The loop is going to rotate with a constant angular speed of 2 pi f. So that means its angular position. So angular position is given by theta equals to 2 pi f times some sort of time t. So therefore, we end up with B pi r squared cosine of 2 pi f t. So taking this, we can move it in to Faraday's law. With Faraday's law, we have epsilon equals to negative d by b over dt. But keep in mind, this magnetic flux here is the total magnetic flux that's changing. We have to figure out the total magnetic flux, not just the flux through one loop or one turn. So we have to say this is going to be equal to 100 turns of just one flux. Where n is equal to 100. So you end up with an equation that is nb pi r squared cosine of 2 pi ft. I'm leaving it as n for now so that we have an equation at the end with all variables, and we can fill in the known values for the last step. So here we have negative, let's factor out all the constants. We have nb pi r squared and then d over dt of cosine 2 pi ft. That is then going to give us negative nb pi r squared minus 2 pi f sine of 2 pi ft, and we get 2 pi squared nbr squared f sine of 2 pi ft. Okay, so now we have our voltage, but now we need to figure out the magnetic strength needed, magnetic field strength needed for a peak output voltage of 170 volts. So that tells us that we need to solve for magnetic field from that equation. Given some values, we know that epsilon max must be 170 volts. We know n is equal to 100. We know r is equal to 0.5 meters divided by 2, because that was the diameter given to us. And f is equal to 1 over 60. So from this, we can rearrange this equation to get B equals to epsilon max divided by 2 pi squared n r squared f the reason why we are not going to care about sine of 2 pi ft is because at max value, sine of 2 pi ft is simply equal to 1 for the maximum value. So then from this, we end up with 170 volts divided by 2 pi squared 100, and then r, which is 0.25 squared, times f, is 1 over 60, and we end up with B is equal to 23 milliteslas. in chapter 8.5, we're going to take a look at inductance. So there are two different types of inductances we'll be looking at. There's mutual versus self-inductance. And then we're going to take a look at inductors in circuits. So what is inductance? There are many different ways to change magnetic flux and thus induce EMFs and currents. We can move a magnet, we can move or rotate the circuit, we can change the current in a circuit, and we consider the relationship of the current to EMF as the inductance. So to better explain this, we want to take a look at the two different types of inductances. Mutual inductance is when a changing current in one coil induces an EMF in another coil. So just like this example over here, we have a changing current over here, which induces an EMF in a second coil. The maximum inductance requires most of the flux from each coil to go through each other. So for example, over here, I have a current and it's going to produce a magnetic field. That magnetic field is going to go through the second coil and thus induce a current that will then have give us an EMF, induced EMF, epsilon 2. Self-inductance is pretty much in its name. It's when the magnetic flux from the current in a single coil or circuit is going to pass through itself. So if the current changes, so does the flux, inducing an EMF. And we call this self-inductance because there's only one coil at play. So we can define self-inductance as the ratio of the magnetic flux through the inductor to the current in the inductor. So L, the inductance, is equal to magnetic flux over some sort of current. In terms of the units, we use Henry because it's Tesla meter squared per amp. So how do we determine the induced EMF of an inductor? The induced EMF in an inductor can be determined by Faraday's law, which we know to be epsilon equals to negative of the magnetic flux over dt. But we also know that L for self-inductance is equal to flux over current, and so we can replace the term for flux with Li. So we end up with negative L di over dt so that we can quantify a change in current and relate that to the EMF within an inductor. So now we want to take a look at inductors within circuits. Similar to how voltage across capacitors doesn't change instantaneously, the current through an inductor also can't change instantaneously. So whereas capacitors are comparable to inductors, we now have voltage comparable to current in this case. So an inductor is usually called what we say a back EMF because it opposes the change in the current. And that's where the minus sign comes from in the equation. So let's take a look at what happens in an RL circuit. So a circuit with a resistor and an inductor. So at time 1, the switch is open and there's no current that's flowing. At time 2, immediately after the switch is closed, no current is really flowing, but the current is non-zero. So over here, we then have an inductor's back EMF being equal to the magnitude of the battery's EMF, which is epsilon naught. So in the next step, what happens after a little bit of time has passed additionally? After some time, the rate of change of the current and the inductor EMF both are going to approach zero as some part of equalization. The inductor is then going to act like the wire. So overall, in summary, as the current is increasing, so does the resistor's voltage, IR. And as the current builds up in an RL circuit, we notice these things. We notice that the current I is going to increase at an ever decreasing rate. Then the change in current results in an EMF in the inductor, and the EMF is going to decrease with a decreasing rate of current change. the EMF from the battery is just going to stay constant, and the resistor and inductor voltages will have to sum to the battery voltage due to Kirchhoff's law. So let's introduce a time constant because it is required for analysis of induced EMFs. For the circuit we just presented, we can use Kirchhoff's loop law to analyze the circuit. So going clockwise, we have a voltage increase at the battery source. We have a decrease at the resistor. We have a change of epsilon L at the inductor, or what we call the back EMF from the inductor. So we have epsilon naught minus IR plus epsilon L equals to 0. If we want to figure out what I is and what the current is, then we can simply have, we can differentiate this equation over here, and we end up with this term for the current, and we have a time constant up here where we have e to the power of negative RT over L. So the goal is to understand what the time constant means. With a capacitor, we characterize time-changing quantities with the capacitive time constant RC, but with inductors, we don't have RC anymore. We have R and we have L. So here, if I go back, we have R over L as the time constant. So it's the constant in front of T. So the inductive time constant is L over R. It depends inversely on resistance, and it means that the lower the resistance, the higher the steady state current, and therefore the longer the time it's required for the current to build up. In problem 5, we're taking a look at a long solenoid of cross-sectional area A and length L with n turns per unit length. We want to find self-inductance. So simply put, the equation for self-inductance, so let's see what we're given. The equation for self-inductance is L equals to magnetic flux over I. But we don't know what magnetic flux is, and we don't know what I is. So we should be able to try and figure out one of these. So if we try to go with magnetic flux, we know that magnetic flux is going to be equal to B dotted with A. We know the field is uniform. We know we have a cross-sectional area of A. And so we are also going to assume that the field is perpendicular to the solenoid coils. So that means we simply have BA cos theta, or this becomes 1. So with this, even if I have magnetic flux, I still need magnetic field. So B for a solenoid is equal to mu naught n times I. So together, we can put everything that we've listed here. We have L equals to magnetic flux over I. We know this is going to be BA over I. We know B is going to be mu naught NIA over I, and we know that the I's are going to cancel out. And we get L equals to mu naught NA. But we're not quite done yet. The flux itself, it was n turns per unit length. There are going to be a total of NL turns. So we have to make sure for our flux equation, prior to adding it into all this, we should have had NL. I'm just going to quickly. So important over here. We have N turns per length. So the total number of turns, in fact, which we call capital N, would actually be NL. So very important to understand that. When we use N in this equation for B, it's the total number of turns that we have, but we're given N turns per unit length and a length L, so we have to figure out the total number of turns N. So in this case, we now have mu naught NLA, which is correct. And that is your self-inductance of the solenoid. Okay, in problem 6, a 5.0 amp current is flowing in a 2.0 Henry inductor. The current is then reduced steadily to 0 over 1 millisecond. Find the magnitude and direction of the inductor EMF during this time. So the equation for the inductor EMF is epsilon L equals to negative L di over dt. So we're already given all this information. We know L is equal to 2.0 H. We know dt is equal to 1.0 millisecond. And we know that di is equal to 5.0 amp. So we could just plug in everything, minus 2.0, and then we have 5.0 amps over 1.0 milliseconds. And that gives us 10,000 volts. And should be negative, but we're just looking for magnitude. And that is our answer. So in problem 7, we have a large electromagnet that's used for lifting scrap iron. It has a self-inductance of 56 henries. It's connected to a constant 440 volts as a power source. The total resistance of the circuit is 2.8 ohms. We're trying to find the time it takes for the current to reach 75% of its original value. So this has to do with time constants. We know that we have to give some thought as to how to approach this. So we're going to start with what we're given. From the equations we looked at before, we know I is equal to epsilon naught over R times 1 minus E to the power of minus RT over L. And we want T when it's 75% of I. So that means we have to figure out when I max occurs. We know that I max has to occur when everything inside these brackets is just 1. So that means we want 1 minus 0 in order for the maximum value of current. So this is our max value. In order to get 75% of this, that means we're trying to find 0.75 epsilon naught over R is equal to epsilon naught over R times 1 minus E to the power of minus RT over L. So then all we have to do is solve and we can cancel out the epsilon naught and R's. So we have 0.75 is equal to 1 minus E minus RT over L. E to the power of negative RT over L is equal to 1 minus 0.75, which is 0.25. We can take the natural log and get ln of 0.25. Then we have T is equal to minus L ln of 0.25 divided by R. And T is going to be minus 56 ln of 0.25 divided by R, which is 2.8 ohms. And that is going to give us 28 seconds as our final answer. So now that we've taken a look at magnetic fields, magnetic forces, we've taken a look at Faraday's law and induced EMF, as well as RL circuits, we want to be able to analyze the magnetic energy and also tie things back to electric fields. So we'll take a look at magnetic energy within an inductor, we'll take a look at magnetic energy density, and then take a look at induced electric fields. So what is magnetic energy in an inductor? Like electric fields, magnetic fields will contain stored energy. In a decaying RL circuit, it basically is synonymous to a discharging RC circuit. So we can make those connections there. Previously, we had this loop equation. If we multiply all the terms by a current I, we get this equation over here. So the third term, Li di over dt, is the rate at which the inductor stores energy. So we call this P. If we increase the current by dL over a time interval dt, we can calculate the total energy stored by integrating du equals to P dt. So we end up with U equals to 1/2 Li squared to get the energy stored in an inductor. So looking at this again, we know that this is going to be in an RL circuit. So the first term is going to show that the battery supplies power to the circuit at a rate of epsilon naught I. The second term is the rate of energy dissipation in the resistor, and negative means that it takes energy from the circuit. And the third term is going to describe the energy the inductor takes from the circuit. It's very important to understand that this inductor does not dissipate energy, but it rather stores the energy in its magnetic field. So in terms of magnetic energy density, in a previous example, we found out that the inductance of a solenoid with a length L and cross-sectional area A is L equals to mu naught n squared AL, where mu naught Ni is equal to B. We can then calculate the magnetic energy stored in the solenoid using this equation that we had before, U equals 1/2 Li squared, and we can replace L with this. So we end up with an equation that gives us the magnetic energy density, UB is equal to B squared over 2 mu naught. So now let's try to make a connection to induced electric fields. We've talked about induction so far in terms of EMFs and circuits, but we should probably try and redefine it in a different way. So for batteries, chemical reactions are going to separate charge, and for motional EMF, magnetic forces are going to separate a charge, and for a changing magnetic field, some sort of electric field in the conducting loop that will separate the charge. So when we talk about an induced electric field, it's going to exert an electric force which causes a changing magnetic field. We'll take a look at that by looking at Faraday's law again. So prior to this, we defined Faraday's law in terms of a changing magnetic flux. But there's actually another way to represent Faraday's law. We can relate electric fields to a magnetic flux. So specifically, we can take a look at Faraday's law, and because it states that a changing magnetic field is going to cause a change, it can also create an electric field. So the integral of E dr is equal to negative d phi over dt. So that's also another way of writing Faraday's law, which relates the change in flux directly to an electric field. Hey, the last problem we're going to go through has to do with MRIs. So there's a huge explanation here. And we start off with superconducting electromagnets like solenoids in MRI scanners, and knowing that they can store a lot of magnetic energy. If we lose some coolant, it can be really dangerous because the current is suddenly left without a zero resistance path and will quickly decay. The result is then going to be an explosive release of magnetic energy, so it's something that you always want to prevent. If an MRI solenoid carries 2.4 kiloamps and has a 0.53 Henry inductance, we want to A, find the stored magnetic energy, and B, find the rate of energy release when it loses its superconductivity. And it gives you a definition of when it loses that superconductivity. It's when the resistance drops abruptly to 31 milliohms. So there are various things to look at here. We'll start with A. Find the stored magnetic energy. We know that the equation for magnetic energy is going to be U equals to 1/2 Li squared for stored energy. We know P is equal to I squared R for the power of the resistor. And we know that the solenoid carries a current of 2.4 kiloamps. So to find the stored magnetic energy, we can just solve 1/2 0.4 0.53, because that's L is equal to 0.53 henries. 0.53 times 2.4 kiloamps squared, and you end up with U equals to 1.5 megajoules of energy. So that's how much energy is stored. Now we want to go and take a look at the energy release. So for the energy release, I'm just going to go down to the next section. This is part B. We already know P is equal to I squared R. We know that I is equal to 2.4 kiloamps squared. And then we know R is going to be, let's just write it in what we're given, 31 milliamps, or milliohms. So that gives us P equals to 0.18 megawatts as our answer. And that is a lot of power. In fact, this is equivalent to about 1,800 100-watt light bulbs. So you can kind of imagine how much power that contains. We're now going to move on to alternating currents. It's the last section of all of this. We're trying to put everything together and tie it back to circuits. So we'll take a look at circuit elements in AC circuits. We'll take a look at LC circuits, so inductor capacitor systems. We'll take a look at damping, and we'll take a look at driven circuits with resonance. So first of all, before we begin any of these discussions, we want to take a look at what an alternating current is. Basically, it's going to be a circuit that involves time-varying electrical quantities and components. So a sinusoidal AC voltage or current is usually characterized by three things: amplitude, frequency, and phase constant. The amplitude is going to be specified by a peak value or RMS. The frequency is going to be specified by an angular frequency, and the phase constant is going to specify where the signal curve crosses zero with a positive slope. So those are the three characteristics of a sinusoidal AC voltage. So we'll look at each of these separately: amplitude, frequency, and then the last one. The AC voltage amplitude is given by its peak value. So we have Vp and Ip for the peak values of voltage and current respectively, or we can call it the root mean square, V and I RMS. The RMS is going to be the average obtained by squaring the signal, taking the time average, and then square rooting that. For a sine wave, RMS and peak values are going to be related by this equation over here. So the RMS for V and I for an AC voltage will be defined as follows. Now for an AC voltage frequency, usually we describe frequency F in terms of cycles per second or hertz. For an AC voltage, because it's sinusoidal, we want to take a look at the angular frequency omega in radians per second or 1 over s. So we use angular frequency for rotational and simple harmonic motion since a full cycle contains 2 pi rad. So we end up with an equation here, which you've probably seen many times before, omega equals to 2 pi f. And that's the angular frequency for AC voltage. Then we take a look at the phase constant. Phase constant indicates when the AC signal's sine curve crosses zero with a positive slope. So the current and voltage can each have different phases, and we can have full equations for AC voltage or current. So essentially, now that we have all three parameters, we are able to craft an equation for each of these quantities. For voltage, we have Vp being the amplitude, and because it's sinusoidal, we have sine of omega t plus your phase constant, providing your phase shift. You have AC current, the exact same thing, but you have Ip sine of omega t plus the phase for the phase shift for the current. So looking back, just remember that everything inside the bracket, if you change something, it's going to be the opposite effect. So going here, if I have a negative phi, then I'm actually shifting everything towards the right. If I have a positive phi, then I'm shifting everything to the left. So that's basic translational movement from calculus courses and functions. So when we take a look and we break down an AC voltage signal, it's a sinusoidal wave. So we have an axis for omega t, and then we have another vertical axis for the voltage. So here we have as time progresses, you have a sine wave with an amplitude. The peak of the amplitude is then going to be Vp for your peak voltage, and then there's going to be minus Vp for your lowest voltage. There is going to be a full period from from this point here to this point here, and so that's 2 pi rad for a full cycle. Now we want to take a look further into resistors in AC circuits. So a resistor R is connected across an AC generator. So keep in mind, we're still taking a look at circuits, but now the battery has been replaced by a circle with a wave. This represents an AC source. And we can calculate the current by using I equals to V over R, same equation for Ohm's law, but we replace V with our equation for AC voltage. So we have Vp sine of omega t over R. If we take the phase shift as 0, then the current and the voltage are going to have the same frequency, and we call that being in phase. So now we want to take a look at capacitors in AC circuits. So we have an AC source, and then we have a capacitor here. If we derive Q equals to CV, then we get dq over dt equals to c dv over dt. We know that this can be represented with I and the capacitor current. So we know V is also equal to Vp sine omega t, assuming phi is equal to 0. So we end up with this equation where I is equal to c, and then we take the derivative of time with respect to Vp sine omega t. When you take the derivative with respect to time, you get cosine, and you can simplify everything and end up with I equals to omega c Vp sine, or Vp cos of omega t, or you can do a phase shift and have sine of omega t plus pi over 2. So that's a trigonometric identity between these two. So what does this tell us? We're going to go to the next slide. So from all of our analysis before, we know that the current in a capacitor is going to lead the voltage across the capacitor by 90 degrees. So that was that shift from before. It means that we can also calculate the amplitude since the maximum value of cosine or sine is 1. So we can make a comparison and we can say the current is equal to omega c Vp because, going back, the maximum current is going to be when sine of all of this is 0 or when cosine of all of this is 0. So Ip equals to omega c Vp will be the maximum value of I. So that is what we call the peak current. If we want to rewrite it in a form that resembles Ohm's law, then we have to define a new term called Xc. So we just call that 1 over omega c, and we can get an equation using Xc, which is called the capacitive reactance. So we're just simply simplifying things and creating a new parameter. So we get I equals to V over R, but the V is now Vp and the R is now Xc. We've gone through resistors, we've gone through capacitors. We now want to take a look at inductors in AC circuits. If an inductor L is connected across an AC generator, we can calculate the induced EMF. So this is Faraday's law. We can replace epsilon L with this because that is the EMF or the voltage from the source. We also know that there's back EMF, so then it's going to be negative of the change. So we just make sure that this is opposite of what is being generated. So then we can integrate to get a relationship involving the current I, After you integrate it, we get this equation, Vp over omega L sine of omega t minus pi over 2. Now, what's important about this is there's another way to figure out the current, and it's through peak voltage, and also with an inductance term. But of course, we want to simplify things. Prior, we had XC for the capacitive reactance. Now we have XL for the inductive reactance. So it's not reactive, but reactance. And to make things simpler, we have XL equals to omega L. So we have the angular frequency multiplied by the magnitude of inductance. So just like the capacitor, no power is dissipated. Instead, energy is alternately stored and released as the inductor's magnetic field builds and decays over time. So here's a summary of relationships. We had taken a look at resistors, capacitors, as well as inductors. We had peak current versus voltage, and we were able to come up with a relationship between each of them for each of these different circuit elements. What each of these tells us is some sort of phase relation. So V and I are in phase when we're taking a look at a resistor. When we're taking a look at capacitors, your current is going to lead your voltage by 90 degrees in terms of a phase shift. Whereas for an inductor, your voltage is going to lead the current by a phase shift of 90 degrees. So think about why that is and use the slides from before to understand why these two relationships are reversed for a capacitor and an inductor. So why does the inductor voltage lead the current? And because if we think about it, a changing current in an inductor is going to induce an EMF. So before the current can build up, there first has to be a voltage across the inductor. So that means the voltage has to happen first, and then it's going to lead by a phase of 90 degrees or pi over 2. So logically, it does make sense for the voltage to lead and be ahead of the current because the current buildup is going to take place after the voltage crosses the inductor. With a capacitor, the current is going to lead because the current has to flow before the voltage changes significantly within a capacitor system. So if you want an overview of the different parameters as well as the different characteristics of capacitors versus inductors, this is a very good table taken from Essential University Physics. It basically covers all of the different types of concepts we covered. So the equations for each, the differential form for each, of any opposing changes in either voltage or current, energy storage, behaviors and low and high frequency limits, the reactance, as well as the phase. So these are good characteristics to know when comparing capacitors to inductors. Next, we want to take a look at what a phasor diagram is. So a phasor diagram is very helpful because it helps to summarize phase and amplitude relations in AC circuits. So you'll always see these when we're talking about AC circuits, and it would be good to be able to explain them in the future. The phasor is the arrow with the following properties. The length is the amplitude of the AC voltage or current. So the longer the phasor is, the larger the magnitude of the AC voltage or current. The angle omega t is going to be the angular frequency. For a resistor, we have this as the voltage resistor or voltage phasor. The current and voltage phasors are going to be in phase and they rotate together. For an inductor, the voltage phasor is going to lead the current phasor by 90 degrees. So you see I and little I over here with omega t, and then you're just going to transform it or phase shift it a certain angle, phi, which is 90 degrees, to get your voltage phasor because the voltage is going to lead the current for an inductor. Now, before we move on to a capacitor, if we think about it, the current is then going to lead the voltage phasor. So that means that your voltage is going to take place before, and we can put it in the fourth quadrant of the Cartesian coordinate system. So we can have the voltage phasor here because the phasor lags the current phasor by 90 degrees. So we're now just going to go through an overview of how LC circuits work, as well as what types of oscillations there are. So an LC circuit has an inductor, here L, and a capacitor. At first, the energy is all electric within the capacitor. Afterwards, the current is going to flow through and reach the inductor. And as the current increases, so does the magnetic field within the inductor. Now, all of the energy has now gone from electric to magnetic. It's now in the inductor itself. After some time, the current in the inductor is going to pile up, and it's going to pile up a positive charge at the bottom of C. So you have the current going through, and we have a positive charge buildup over here at the bottom. What happens next is the capacitor is going to be fully charged, but opposite of its initial state. So you'll see that this has been reversed. So the energy is now all electric within the capacitor. Now what happens next? Since all of the energy is in this capacitor, the current is going to go from the positive to negative terminal. So now the current is going in the opposite direction, and the capacitor begins to discharge. And now it's counterclockwise. Once again, the current is going to flow through the inductor. There's going to be a magnetic field. All the energy will be converted to magnetic energy once again. And then, of course, the positive charges are then going to pile up on the top of the capacitor this time. And all of the energy will be converted to electric energy. Now the capacitor polarity has reversed. You have positive charges on the top side and negative charges on the bottom side. And then the whole circuit is back to its initial state, and it repeats over and over again, assuming there's no energy loss. So what is an analogy to the LC circuit? An LC circuit is the electrical analog of a mass spring system. So energy basically goes between the magnetic and electric components, the inductor and capacitor, and it's basically like an oscillation, and every oscillation is going to have a frequency. So that means we should be able to analyze the frequency of an LC circuit. So to do this analysis, the total energy in the LC circuit is going to be the sum of the magnetic and electric energies. We have two equations for that from before, so we can just write them out. In an ideal LC circuit, this is going to be conservative, so that means if we derive it, then the change is going to be 0. So we set it to 0, and then we derive these two terms, and we get this equation. Of course, what we want to be able to figure out is the angular frequency. So we have to pull together all of the knowledge we've learned in previous slides. We know V is equal to Q over C. We know that dV over dt is going to be equal to this. We know an equation for I. We know the derivative of that as well. So we can rewrite the equation we had before and end up with this. If we solve this differential equation, we're going to get a value for Q, and Q is equal to QP for the peak charge times cosine of omega t. From that, we're able to determine what omega is, and we end up doing some replacements, algebraic manipulations, and we end up with 1 over the square root of LC for our angular frequency. But that's not what happens in real life. In real inductors, capacitors and wires are going to have resistance. So we have to take a look at RLC circuits instead of just LC circuits. So from our previous analysis, we only had 2 terms. We now need 3 terms. And the last term is going to be the rate of energy dissipation, which is going to be proportional to the amount of power. So we have I squared R. So we get a different solution to the differential equation. No need to show the work, but we end up with a decaying oscillation amplitude where we have RT over 2L. Next, because we know that there is resistance within all circuits, ending up with RLC circuits, we have to take a look at damping and what it means. Oscillation damping occurs when you introduce a resistor. Basically, as the resistance increases, so does the damping effect. Critical damping basically means when the circuit quantities are going to decay to zero without an oscillation. And this occurs when your time constant is equal to 1 over omega. So it's important to avoid this since in order to get the strongest signal, we want to minimize the effect of the resistor and we want to minimize the effect of damping. So from all of this, we know that the goal is to prevent too much damping from occurring. So in the next slide, we're going to be talking about how we can counteract a damping effect. And that's by introducing a driven RLC circuit. If we create a driven RLC circuit, it means we've added an AC generator. It helps add an external driving force on the oscillator to help counteract any damping that occurs. So if you've ever heard of a driving frequency before, that comes from an AC generator. It creates a frequency omega D for a driving frequency. And there's going to be a resonance behavior at the undamped natural frequency of omega naught. So at resonance, the C and the L voltages will cancel, but this is a way to help reduce the effect of damping within an RLC circuit. So just as a summary, we're going to cover the important equations that we learned in this chapter. We took a look at magnetic flux and its definition. We then took a look at the magnetic flux over a flat area, BA cos theta, Faraday's law, where the negative sign comes from Lenz's law. We have the equation for self-inductance. We have an equation for the EMF coming from an inductor. We have the energy stored in an inductor. We have magnetic energy density, and we have Faraday's law. And this version of Faraday's law compares the magnetic flux to the electric field. So to sum everything up from our discussion of electricity and magnetism, we have our key equations known as Maxwell's equations. So we have Gauss' law for an electric field, Gauss' law for a magnetic field. This basically means that all magnetic fields going out must come in. Faraday's law, as well as Ampere's law. So all four of these are Maxwell's equations and help tie electric fields to magnetic fields so that we can analyze electromagnetism altogether. So that is actually the end of our chapters on concepts for this course. We're now going to move on to specific applications like MRIs and different techniques like NMR that are based off of electromagnetism.